Okay, so before we start, well, actually, as we start, I'll introduce myself. My name's Mike. Most of my career I've spent making large-scale embedded systems, which is in the oil and gas industry, different kinds of tools and technologies that were used in the oil field for finding oil, drilling for oil, these kind of things. And as my career progressed, I ended up more into the organization of teams, more in facilitating the teams to deliver software faster. Got very interested in the XP methods, but test-driven development, especially around hardware and software and all these things. And eventually that led to my career in what you could term continuous delivery. So how many people here are working with embedded systems at the moment? Or native code at all? Okay. So feel free to stop me at any time to, if I get too embedded for people. So I usually start with a little bit of an introduction about what continuous delivery is. I'm not sure I need to do it here at this conference, but the point is that you want to get changes of all types to the user. And that's a great ambition. It's a little bit different path you need to take to be able to do that in embedded software. And that's what I want to talk about today. The needs and the drivers, especially the business drivers, are very different in embedded systems than they are in more traditional kinds of software. So I'll try and dig into some of that stuff. But the concepts themselves are just as easily transferred into the world of embedded, and that makes me very, very excited. So embedded software, normally it runs on some hardware, which isn't actually very different from any other kind of software, right? It's running on some hardware. It might be an AWS, on a virtual machine, in a container, whatever, but eventually it's going to run on software. Somebody's writing code that talks to hardware at some level in any software system. But embedded software is a little bit different because it's very, very close to this hardware. A typical example would be your washing machine. It's got some software in it, very simple stuff. It probably doesn't do a lot of continuous delivery. But there's lots of different types of safety critical embedded software, especially in places like medical, where you have different kinds of needs and different kinds of regulatory requirements. And then there's automotive. Self-driving cars are a very hot topic now, but even a traditional truck from any given truck manufacturer will have over 1,000 microprocessors in it, doing all kinds of things, the braking systems, acceleration. There's a lot of software going into automotive. Oil and gas, obviously, and just industry in general, mining, these kind of applications require an awful lot of embedded systems, and they're also often very safety critical. There is software in rockets, but that never goes wrong, so that's fine. Some of the differences that you typically get in embedded software, one is that obviously it's hard to get your own rocket to test the software. That can be a challenge. Even if you're working on washing machines, it's not very often that every embedded engineer will have a full production-like environment on their desk. So access to the production-like environments is actually quite a challenge. Many systems I've worked on had to have a support lifespan for more than 20 years. If you're talking military use, it's often more than 30 years the software has to be supported for. I was talking in Jutland last week, and I had a room full of embedded software developers, and some people in the room were maintaining software that was 23 years old. And that's not unusual in this world. Very often safety critical or regulated markets. Release costs can be high. Release costs can be extremely high. Sometimes it can be business critical if you have to make a release. And we'll talk a bit more about that later. Deployment is different. We can't use Octopus deploy or anything. We can't just use some Ansible. We have to actually do something custom for any type of system we're making. There isn't any off-the-shelf tools for that kind of stuff. Sometimes we need a full audit trail like you would in Sarbanes-Oxley. And very often the deployment matrix is very, very wide because it's rare that you make a product. Typically you'll make 16 different variations of a given product that are almost exactly the same, but are not exactly the same. So we have what's called a maturity model for having discussions with people about continuous delivery. Everybody has a maturity model. This is mine. But the point is that this is designed for just general continuous delivery, just talking about how organizations deliver change to customers. So the things I want to focus on in this talk are about how artifacts are managed, how we enable a full trace of the software we produce, how we do versioning. It's very important in embedded systems. And of course, the architecture and design aspects of dependency management, individually releasable components, and again, we get this full audit trail. I'm also going to talk about a small Gradle plugin we produced that we use to help enable some of this traceability and so on in the software. So the first thing that we would start with an embedded team is just lay the standard foundations that you would expect in any development team. Standard continuous delivery playbook. Because very often in the embedded world, this is the build process, right? Somebody presses F5 and a binary is produced and it goes in a manufacturing system. And that's the process. That's okay when you're one person doing prototype work, but it's not a way to produce binaries that are going to, for instance, self-drive your car. So very simple stuff. Introduce version control systems. Some places still don't have version control systems. Talk about how to do automatic build, automated testing, just some very basic things. And then once that's in place, you need to kind of build some development process around the way the teams work. So we want to, was anyone in the last talk in this room? So it's very much about how to break the dependencies down and limit the number of builds. And we want to do the same thing in embedded systems. And it's not because we necessarily want to avoid rebuilding things that don't need to be rebuilt, but retest and requalification can be very, very expensive. So if you can avoid that, it's very, very powerful. So, I mean, basic things, you're making components, you want the integration and testing of them to be automatic. You want all the binaries to be fully traceable. You want to know where they came from, maybe what Git SHA produced them, what build job created them, and those kind of things. And you want these artifacts to be managed in some kind of system that understands versioning. And you want to build all of that stuff actually into the binary, so that if you get a call from someone at a supplier who says that this car is driven off the road, you want to know exactly which version of the software has been running on that car. And again, the release principles are necessary as well. It's about bringing in some discipline into the development environment. We want to make sure that release is a manual decision. We don't want to accidentally release software. That would be a disaster. We want to make sure that release binaries can only depend on released components. So again, we have this other kind of manual step. And we want to be able to maintain any release we've produced. So that means if we have an application with multiple components that we ship from 3 years ago, if someone calls us up, we need to be able to fix and patch any part of that component. So the first step is, first of all, making sure that you build the versioning information into the binaries that you produce. A simple way to do that is just generate some header files in your build process. And then you can even get your software to be able to take that back. But if you do just enough to get that information in, you can even just use a simple tool like strings to be able to find the versioning information from any binary that's shipped. And the second test is, okay, now that we've produced binaries that can identify themselves, how do we make sure that we can reproduce them if we need to, we can patch them? And that means we need to put all the tools that the binaries require to be produced in some kind of versioning system too. Like, we could use an artifact management system. You could even use a shared disk as long as there's proper permissions and that no one can change it. It's kind of read-only. That's fine. But the idea is that if you want to be able to reproduce something that was made 3 years ago, you need the exact compiler. You need the exact libraries. You need the exact system library path. All these things matter, and you need to have them in a way that's versioned so that you can branch them. Now, if you're doing your builds on Linux, then a simple way to make this kind of much more portable and much more easier to manage is to use tools like Docker. Put your tools and your complete and build environment inside a Docker image. And then you can be sure that the developers, the testers, you yourself in 2 years are using exactly the same systems. I like to tell this story. This is Life Over. This is a friend of mine. He's actually my programming hero. I first met him when I went to Norway, and we were on a project together. It was a rapid response project to fix a critical issue in the field. I was working on a different part of this, but the crux of the story is that we had this kind of router, a fiber optic router, and every so often they would crash. Not very often, but often enough. And if we have 10,000 of them that you're dragging behind a vessel in the North Sea, it would happen enough to impact the business. And talking millions and millions of dollars every day that these things happen. Now the problem is we only had one of these routers in the office, and it hardly ever happened on one router, but it happened quite frequently when you have 10,000 of them. So he spent 3 months just being able to reproduce the bug. And it was the strangest thing, because if he moved a log message, he moved even just a comment that would reproduce this bug or not reproduce this bug. And it turned out that what was happening to crash the system was that a forever loop that was supposed to never ever exit would suddenly just exit and start executing whatever instructions were running after it. And then the system would go haywire. So 3 months just to figure out, okay, we can reproduce it. Another 3 months to figure out that that was what was actually happening. And it turns out that it was a combination between the compiler and the real-time operating system. So the compiler vendor had gone out of business. The real-time operating system vendor had been bought by another real-time operating system vendor, and their product was discontinued. And that was really unfortunate, because the cause of this error was that the real-time operating system didn't save one register properly during context switching, during interrupts. And that register had one bit that a compiler would output, which would tell whether or not to exit a loop. So, kind of stuck. Now, both the compiler vendor, both the compiler and the real-time operating system were closed source binaries. No access to support. This was I guess the system was at least 10 years old at this stage. Still in production now. It's probably going to have another 10 years. So it's probably going to have 30 years in the field. But we don't have access to any of them. Now, it turned out that in that routine that was saving the register, Life could find that routine in the binary. And there was just enough space. There was a few no-op instructions at the end of the routine that he could do something. And what he did was he patched the binary with like 4 instructions to save that register. So he spent 1 year to write 4 instructions in a binary file. And I always tell the story that like Life Over is my programming hero. He wrote 4 bytes in 1 year. But I mean, it was really inspirational to work with a guy, because I mean, to see that kind of determination, to be able to see that through, was great. But there is another story, like a moral to the story is, I mean, closed source operating systems, closed source startup files, closed source compilers, closed source libraries. They're a risk. They're a risk to systems that you're expecting to have longevity from. So if you're thinking in the timeline of decades, then you have to really, really think hard about the dependencies you take into your system. Just as a idea, how many of you are working on a software system more than 5 years old? More than 10 years old? More than 15? Okay, how long?
20-something.
20-something?
Nearly 30.
Nearly 30. It happens, right? We have these systems. They're core infrastructure to some places. We have to think about this stuff. Okay, so now you've got your tools, your build process, reproducibility, your traceability. And the next step is, okay, how do we make sure that the thing we actually built is any good? And that's like when we start to thinking about the safety of the software we're making. We want to try and build quality into the product rather than trying to glue it on later with QA and manual testing processes. Because guess what? In 10 years' time, who's going to be able to run that test plan? Nobody. It doesn't exist. So in complex systems, adding more inspection steps and approval process increases the likelihood of future failures. But this is how we tend to approach things, where we have, especially safety critical, all these things. Even SEAL 2, a lot of the legislation and safety critical things that we have to follow is just adding a lot of manual steps. Or generally that's how they're implemented, as manual inspection processes. And it would be much, much better if we could turn that into some kind of automation. So obviously I don't have to preach to the choir about TDD, but I mean, this is quite new in embedded systems. Not many people are doing this, but there's no reason not to. I mean, you can do TDD on kernel modules, you can do TDD on RTOS, you can do TDD on interrupts. You can do TDD on any part of an embedded system. It's just about having the will to do it and understand that you have to learn the techniques. That's great, but what does TDD really give you? Does it tell you you're not going to crash the car? Not really, right? I mean, at best, TDD can make sure that you wrote the code that you thought you were going to write, which is helpful, and it can save a lot of errors. But you need some other kinds of testing. You need to have some system-level testing. And for us in embedded, that system-level testing usually involves hardware-in-the-loop testing. So we need to solve a lot of very custom problems. Like we need to be able to switch power. We need to be able to flash devices. We need to be able to attach oscilloscopes to test points. We need to be able to do all kinds of rare things that is actually quite challenging. One of the companies I work for in Oslo, they make this really cool ASIC, and it's a very, very low power radar. So you can do all kinds of fun things with this radar, but one of the applications is to do detecting people, and it does it by detecting basically breathing. It's a breath detector. It detects the rib cage going in and out with breath, and it's got kind of a lot of medical uses, like for instance on burns victims, monitoring their breathing, and premature babies. And in my first weeks there, they were testing baby monitoring. So I got my sister-in-law who'd recently had a baby and all her friends to come into the office. And you know, we did all these kind of tests with all these babies screaming, crying, sleeping, all kinds of noise in the office, and lots of data was collected. It's kind of hard to reproduce that kind of test, but it was still very valuable because the data sets collected could be run and run and run again against the software, so you can look for deviations from expected behavior. But they thought, that's not good enough. We need something a bit more deterministic than this. So they have this guy called Stig. He's a PhD in signal processing, very, very smart guy. And he came up with this idea that he said, to the radar, if I rotate a ball bearing at a certain speed, it looks just like a chest cavity. And if I use a smaller ball bearing, it looks like a premature baby. If I use a big ball bearing, it looks like an adult. So why don't we get some Lego, which doesn't have much of our radar reflection? It's plastic. Why don't we just start rotating ball bearings and attach that up to Jenkins? So they've got a whole lab full of like these Lego robots. There's people there paid to play with Lego all day. So they go and like you make a commit, all the unit tests, integration tests, packaging, deploy onto the hardware, and then all of a sudden like these ball bearings start dancing around. It takes some investment to do this. So there's no shortcuts in this, but it's still super valuable. It's the most valuable thing you can do for your embedded systems. And if you have any kind of quality bar that's high and you're dealing with complex environments, it really is worth the investment. Yeah, actually, I'm going to come clean here. Normally, we talk, oh, you should use static and dynamic analysis. I really don't think it's that valuable, to be honest. It's, and I always say this is the last thing you should do, because a lot of places I go, oh yeah, let's get the tools in, let's get all this insight into our systems. We're going to fix the things the machine tells us to fix. This isn't going to help you know if your car is going to drive off the road. This isn't going to help you know if you can still detect a premature baby breathing. It might help you with doing watching out for some low-level errors. The thing is, you should do it, but you should do it last. Do it last after you've installed all the test benches, all the quality assurance that you can around what you actually care about. And the reason is, has anyone read this book? It's a really great book. And it applies just as well to embedded software as to object-oriented software. Sometimes you can have object-oriented embedded software. But the point is that you need two kinds of testing, right? You need the full systems testing, and you need the unit and very low-level detail testing. And the reason is because they give you different types of feedback. Unit tests give you a lot of feedback about the internal quality of your system, right? They tell you if it's easy to understand, it's safe to change, you've written the code you expected to write. It tells you a lot about living in the code base as a developer. It gives you almost no feedback about whether you can detect babies breathing. But on the other side, the system level testings can tell you an awful lot about the system behavior. Can I detect babies breathing? Doesn't really tell you if the code is easy to understand, safe to change. So you need both kinds of testing because they give you two very different kinds of feedback. Okay, so you've got your build process under control, you've got your quality process under control, then you want to start thinking about how do I go faster? How do we make the team produce software faster? How do we optimize the flow? One of the challenges, if you're making trucks, seismic systems, any kind of consumer product, in fact, is that you're going to have lots and lots of variants of your product. You're probably going to write you're going to have one code base for the entire family, though. Now, when I saw this first, I thought, oh, that's not so bad. Because, I mean, in reality, most embedded software you've got 50, 100, 200, 1,000 different variants of the hardware platform, of the software platform, of the feature set that you're going to ship into the device. So it's a very real problem. How do you test across 100 different devices? It's really hard. So this is where we get to the build and test avoidance. We want to be able to say, okay, if we have a DSP library that's going to do pulse Doppler or something, let's take that out. Let's make it a little Lego brick. Let's make it a component. Let's test the hell out of it and make sure that it can do these things. And then after that, we're going to put it in all the different products that need it. We don't have to test pulse Doppler here and test pulse Doppler here. We just have to test that this is going to make the Millennium Falcon. This is going to make the helicopter. We don't need to go through those system tests. And that's basically the crux of the issue. So one way to do that is, well, first, you have to identify your components and make sure that you can build an API around them. It's very similar problems that you have when you're trying to break a monolith into microservices. Like, Where are the boundaries in the system? Where can I lob off functionality? And how can I give this its own individually releasable life cycle? So one way to do it is to, well, take your libraries, make them their own build pipeline, put them into an artifact management system like Artifactory or Nexus or what have you, and just keep putting them out there. When you want to cut a release, you make a release version of the library. Put it in your release. Well, that's a typo. Yeah, but so you put it in your release repository. Pretty standard stuff for Java developers, I think. Pretty standard stuff in the industry, but this isn't really very common in embedded. And then, well, the most important thing is, how do I maintain this thing that I shipped 2 years ago, 4 years ago? Because it's all very well to have this release train. That's ideal. That's the best if you can have a release train and just have one line of history. But if you've shipped a product that's been flashed into a binary from 2 years ago, and you might have commitments to be maintaining that software for a very, very long period, you have to be able to go back to that point in time, be able to rebuild anything from that, make any patches you need, do that testing locally, and when you're happy, cut that release. And then you want to make sure that any downstream applications that need to be retested, redeployed, republished, however you send your software to the customer, make sure that anything that depends on this will be rebuilt, retested, and then sent to the customer. It's not much more complicated than that. And this is what the Gradle plugin that we have kind of helps with, but you don't need a Gradle plugin. Most of this can be done with a few simple shell scripts. It's just about getting the right ideas about how you manage versioning. So another thing that is quite common is that you want to take, for instance, you have a board that has multiple processors, different things happening on it. You want to turn that into a product configuration with that version of the DSP software, this version of the application software, this version of whatever comes. You want to turn that into something that you individually release and deploy based on components. And like I said, you would be testing the helicopter, not the Lego bricks here. So you might just stick them together in a tarball and then put that into a separate artifact repository. And quite often you would want to put that through the different stages of your qualification process. In automotive especially, you have quite lengthy qualification processes that go through many teams. So this is quite a common pattern to solve that. And obviously, the things that actually get commercialized, there's far fewer of those than actually go through test and so on. So that's really it. There's some things you can do if you really, really aim high. One is that you might not want to have this snapshot release dependency. Maybe you want to be able to potentially release anything you produce. That's really great. Do that. We found it requires more work. You have to be able to automatically generate new versions and make sure that you can have some semantic versioning about how that packages together. But that's one thing. So then you don't have the snapshot repository. Sometimes you want to take a look at your hardware process. This radar company, Novelda, we helped them automate their ASIC development process too. So it turns out that the ASIC development is just like software development in a lot of ways. They are writing code. And they have actually really, really high quality test benches. I mean, they have 97% coverage on their systems because guess what? They can go through this loop on a daily basis and check the quality of their ASIC. But released to them is a very expensive process because that means taping out silicon in Asia and committing to hundreds of thousands of units perhaps. So yes, it's still very much waterfall. So it's kind of, you've got the fast loop in the development process, but at the end, you're making hardware. It's going to be expensive. You want to make it right. But at least during the development phase, that is actually 90% of their time, you can go very fast. Right. That was it, really, on the technology. Just want to wrap up with the story. Tesla is very popular in Norway. I don't know how well that transfers to the UK market, but there's this famous story about the owner who was on the hill. I guess he lived in San Francisco. At the traffic lights, takes his foot off the accelerator, off the brake, puts his foot on the accelerator when the light goes green. The car goes back a bit before it goes forward. And he was on the product forums going, this is supposed to be a luxury car. Why don't you have the hill start feature? Lots of luxury cars have a hill start feature. And that went through product marketing and eventually the engineering teams, and I hope it was tested. But one morning, this driver gets into his car and his software's been updated. And guess what? He's got the hill start feature. Isn't that nice? That's not typical in embedded systems. But it's becoming more and more typical. It's the way the industry is going, not just in automotive, but in all kinds of areas. Actually, I saw this tweet this morning from Rob Smallshare. I don't know if a few of you know him. He had exactly the same thing. He's like, I don't know. I've parked a car. I don't know what kind of car I'm going to get when I get back, but it's going to be different from the one I parked. And this is the future we're facing. There's a downside to this stuff. Sometimes, software, IoT, all these things, there are some risks. But if you digging into the story, I mean, being able to release quickly and efficiently and effectively with high quality actually reduces a lot of risks. In this case, Tesla were able to respond to the information the security researchers had given them and get a fix out there really quite quickly. And that's not true for companies that can't do that. It can be a very expensive thing if you need to recall all your vehicles. So I guess nothing more difficult or challenging than any other kind of software, but embedded you have to have different viewpoints on the future and time, and the technology you have to work a bit harder for because it's very custom. But that's a little tour of embedded software.